So today we're going to talk about how to do the worksheet. If you don't want to watch the lecture, the worksheet summarizes all this material for you, and you can just do the problems at the end. So the atomic nucleus is made out of protons and neutrons. Protons have a positive charge, and neutrons have zero charge, and they have very similar but not identical masses. The atomic number Z is a count of the number of protons in the nucleus. So for example, in chemistry, when you say carbon is number 6 on the periodic table, that means it has 6 protons in its nucleus. The atomic mass number counts the total number, the total number of nucleons, where nucleons is neutrons plus protons. So the number of neutrons, N, in the atom is the atomic mass number minus the number of protons. So it's A minus Z. When we describe a nucleus, we write down a certain chemical notation. So we write down the symbol of the element. So for example, it could be carbon 6. As a subscript in front of it, we write the number of protons. And as a superscript in front of it, we write the atomic number. So for example, for nitrogen, that has 7 protons and 8 neutrons, we write N with a subscript of 7 for the protons and a superscript of 15 because 7 plus 8 is the total number of nucleons, which is 15. Now, different nuclei with different atomic symbols, so with the same atomic symbol, can have different number of protons, and that will make them an isotope. So carbon, for example, you've heard of carbon-14 dating, I'm sure. Carbon normally occurs in nature as carbon-12 with 6 protons and 6 neutrons, but there's about 1% that's carbon-13 with 7 neutrons, and a much, much smaller percent that's carbon-14 that has 8 neutrons. Elements with more than 92 protons, which is uranium, do not exist in nature. They are only formed in the lab for very short periods of time or during nuclear reactions. So what are some other things you need to know about the nucleus? Well, we can estimate the nucleus size. It's about 1.2 femtometers, 10 to the minus 15 meters, times the number of nucleons to the 1/3 power. The nucleus also has a spin, which depends on how many nucleons are present, and an angular momentum, just like the electrons do that orbit the nucleus. And throughout the next 2 chapters, we're going to use a new symbol, U, which is something that's similar to the mass of a nucleon. So 1 U is defined so that the mass of carbon-12 is exactly 12.000 U. So if you look at the bottom, you can see that 1 U is 1.66 times 10 to the minus 27 kilograms. And so the mass of a proton and the mass of a neutron are very slightly bigger than 1 U. And we can also express it in a different set of units that we'll talk about why in a minute. It's 931.5 MeV per c squared. So why does the nucleus stick together? Because remember, we've got protons all forced in very close to each other, and protons are positive charges that push away from each other by the Coulomb force. Well, it turns out that the total mass of the nucleus is less than the mass of the nucleons that make it up. Remember, we said carbon-12, which is made out of 6 protons and 6 neutrons, has a mass of 12, but we said that each proton and each neutron has a mass bigger than 1. So how does that work? Well, it turns out that the energy difference between the mass of the nucleons all put together and the mass of the nucleons when they're separate, that gives us the binding energy of the nucleus, the energy that it takes to pull that nucleus apart. The larger the binding energy per nucleon, the more stable the nucleus is. So if you look at that graph on the side, you can see that around iron and nickel, the transition metals, those are the most stable nuclei. They have the highest binding energy. And as we go out to higher atomic number, it decreases. And as we go down to lower atomic number, down to hydrogen, it also decreases and becomes less stable. So how do we calculate the binding energy? Well, the binding energy is the difference between the mass of the atomic nucleus and the mass of the nucleons, and then multiplied by c squared. Why do we do that? Remember Einstein from a couple of modules ago, E equals mc squared. So we take that mass difference, multiply by c squared, and that gives us the binding energy. So if you have a nuclide, remember a nuclide is just a fancy name for a different nucleus that has either too few or too many neutrons compared to the number of protons, it'll be unstable. So when you have small atomic numbers, so you start at the bottom of the periodic table, it's usually most stable if there's about the same number of neutrons as protons. And if you look at the graph on the side, that dashed red line is a line that shows you where the number of neutrons is equal to the number of protons. As we get to higher atomic number, you can see that it starts to diverge from that. We have to pack in more and more neutrons. And finally, when we get above z equals 82, we can't add enough neutrons to stabilize it. There's just too much repulsion from all those positive charges close together. And so the nucleus size is larger than the range of any force that can hold the protons together. So let's do a sample calculation. So let's find the binding energy for hafnium. So this is a hafnium alloy, so a hafnium isotope that has 180 nucleons. Hafnium has 72 protons. And we're told that the mass of the nucleus is 179.9465 U. When you do these calculations, it's important never round off the U's because they're very, very small differences in the end. And if you round off before you put the numbers in, you're going to get the wrong answer. All right, so the binding energy is the mass of the atom, so that's 179.9465 U. We're using the atomic mass unit for mass, minus the mass of the nucleons. So what's the mass of the nucleons? Well, we know we've got 72 protons, and we can calculate how many neutrons we have by subtracting the number of protons from the number of nucleons. So we do 180 minus 72. That gives us 108 nucleons. And so the mass of the protons is 72 protons times 1.0073. And the mass of the neutrons is 108 neutrons times 1.0087. And so finally we can calculate our binding energy. So our binding energy is the mass of the atom, 179.9465, minus the mass of the protons, 72.5256, minus the mass of the nucleons, 108.9396. So we get minus tells us that it's an attractive energy, that it's binding energy, minus 1.518 atomic mass units. And now we have to do E equals mc squared. So what we're going to do is we're going to put in this conversion factor in between, that 1U is equal to 931.5 MeV per c squared. So when I take that MeV per c squared and I multiply by c squared, the c squared in the denominator and the c squared in the numerator cancel out. So I never actually have to multiply by the number for c. So I just get the mass difference in U, multiply by 931.5, and I get minus 1414.7 mega electron volts. So that's about 1.4 billion electron volts. So that's a fair amount of energy that's holding the nucleus together. If I convert that into binding energy per nucleon, dividing by the number, that's the superscript, so that's our 180, I get minus 7.86 MeV. So in any nuclear process, we have to conserve a few things. So we have to conserve energy, we have to conserve momentum, we know that from Physics 1. We have to conserve the total number of nucleons, and we have to conserve the charge. So A and Z have to be the same no matter what the nuclear reaction is. So we're going to look at three different types of nuclear reactions. ones that produce alpha particles, beta particles, and gamma particles. So an alpha particle is a helium nucleus. It has a positive charge. A beta particle is either an electron or a positron, and a gamma particle is just a ray of light. So an alpha particle is a helium nucleus with no electrons on it. So it's got 2 protons and it's got 4 nucleons total, so 2 protons and 2 neutrons. So it has a mass that's slightly bigger than 4 atomic mass units. It's got 4 nucleons in it. And it has a charge of +2 times E. So in an alpha decay, what happens is that an unstable parent nucleus splits into 2 parts. And as it splits into 2 parts, the parts it splits into is a big nucleus plus an alpha particle. So what happens is we start off with a nucleus N that has Z protons and A nucleons, and we're going to subtract 4 nucleons from it and 2 protons that are going to form the alpha particle. And so the new nucleus that gets formed is going to have 2 less protons and 4 less nucleons. So it's going to be 2 places lower in the periodic table. So we're going to release energy in this process because the alpha particle is going to go flying off with some energy. And that kinetic energy is going to be equal to the energy that's released, which we can calculate by the mass of the parent minus the mass of the daughter minus the mass of the alpha, and then times c squared. In beta decay, there's 2 types of beta decay, beta minus and beta plus. In beta minus decay, a negatively charged particle, an electron, is emitted. And in beta plus decay, a positively charged particle called a positron is emitted. A positron has the same mass as an electron and the opposite charge, so it has a charge of plus E instead of minus E. In beta minus decay, what happens is the neutron turns into a proton plus an electron. Remember, a neutron has 0 charge, so if it turns to something that has a positive charge, we have to also create something with a negative charge so that charge is conserved. In beta plus decay, a proton turns into a neutron, so a positive charge goes to 0 charge, and so we have to also emit another positive charge to conserve charge. And after looking at the energy, they found that the energy and momentum weren't quite conserved unless they accounted for another particle, which they called a neutrino. It's called a neutrino because it has 0 charge, and it's very, very difficult to detect. It does not interact very well with matter, and in fact, it took about 80 years after the neutrino was first hypothesized before someone actually proved that it existed and that it has mass. So the 2 beta decay formulas are for beta minus and beta plus decay. So for beta minus decay, we have a neutron that turns into a proton. So our Z number is going to increase by 1. We have 1 more proton, but we still have the same number of nucleons because all that happened was one of them turned to another kind. And then we're going to emit a electron, and we're going to emit a neutrino. And you see this neutrino has a bar on it. That means it's an antineutrino. So sometimes you see this written as an electron is written with a -1 for the charge and a 0 because it has a -1 charge and it has 0 nucleons in it, and a neutrino has 0 of either. And so if we add up the numbers in the subscripts on each side, you can see that we get Z on the bottom and A on the top. So Z is conserved and A is conserved. In beta minus decay, you move up 1 element in the periodic table. In beta plus decay, we have a positron emitted as a proton turns into a neutron. So when a proton turns into a neutron, we're going to move down 1 element in the periodic table. Our Z is going to decrease by 1. our atomic mass number is going to stay the same. All that we had was one turn to another type. We emit a positron, and a positron, we use the symbol E+. And again, sometimes you see that written with a +1 for the subscript and a 0 for the superscript. It's got 0 nucleons, has a charge of +1. And then we emit a normal neutrino, which has 0 charge and 0 nucleons. So for beta minus decay, you move down one element in the periodic table. And these symbols here, X and Y, we substitute what the symbol is in the periodic table for that atom. In gamma decay, what happens is just that a nucleus is in an excited state. So usually it's just been formed from an alpha decay or a beta decay, and it's not in its most stable ground state. And so when it drops down to its most stable ground state, it loses some energy, and it emits that energy in the form of a high energy photon. And these have very, very high energy, like 1,000 to 1,000,000 electron volts, compared to the hydrogen atom, which is only 10 electron volts. So it's just very high energy light, essentially, that is emitted. So when we look at the reaction equation at the bottom, you see that nothing changes in there. The only thing that changes is that we had an asterisk beside the nucleus initially that indicates that it's not stable, that it's a high energy state. And on the other side, we have the same nucleus, just without the asterisk, plus a gamma particle. And a gamma particle has 0 charge and 0 nucleons. Okay, so let's do some sample decays. Okay, so I've got 23490 thorium, and it's going to something that we have to figure out, plus an alpha particle. So it's an alpha decay. So we have to balance the number of nucleons, and we have to balance the number of protons. Okay, so we know an alpha particle is 4, 2. And so we've got to figure out what is the A and what is the Z. So I've got 234 is equal to A plus 4. So we balance the superscript on each side. So A is equal to 234 minus 4. So A is equal to 230. And if we look at our Z, we have 90 is equal to Z plus 2. So Z is equal to 88. So we jump 2 spots down the periodic table. And if I look at my periodic table here, 88 is radium. So our unknown nucleus is 23088 radium, which is also just called radium-230. All right, let's do a beta minus decay. So for a beta minus decay, we don't know our initial starting, but we know that we have a nitrogen 14 nucleus produced, an electron, and an antineutrino. And so let's write in for the neutron, for the neutrino, that it's 0, 0. For the electron, it's -1 and 0. And then just balance the charges. So we have A is equal to 14 plus 0 plus 0. Or you can just remember that for a beta decay, A is constant, so it doesn't change. Z, if I balance the subscripts, is 7 minus 1 plus 0, which is 6. So for beta minus decay, I step down 1 spot in the periodic table. So my Z is 6, so that means I have carbon. So it's going to be carbon with 14 nucleons and 6 protons. So to complete the reaction, this is going to be what I started with. All right, let's do a beta plus decay. So for a beta plus decay, we have We're going to start with tin 100, and we're going to emit a positron and a neutrino. So let's again do our subscripts and superscripts on those other particles. So a positron has a charge of +1 and 0 nucleons. Neutrino has 0 charge and 0 nucleons. So if I balance these, we get 100 is equal to A plus 0 plus 0. Or again, just remember, for beta decay, A stays the same. We have 50 is equal to Z plus 1 plus 0. So Z is equal to 49. For beta minus decay, I step down 1 spot in the periodic table. All right, so for beta plus decay, I step down 1 spot. So I started with tin. I can move down to indium. So I've got indium 49 with 100 nucleons is going to be what my daughter particle is. Remember, for the exam, these decay equations won't be on the formula sheet, so you need to memorize them. All right, so your active learning problem for today is just to do the questions from the worksheet that's up in the Canvas module. And I've got them all gathered here if you don't want to read through and find them. So first of all, write the symbol for the isotope of potassium that has 19 protons and 17 neutrons. Secondly, how many neutrons are there in boron 11? Calculate the binding energy of 139 lanthanum. And then complete the decay equations. Make sure you include all the neutrinos, all the particles that are emitted in steps A through D below.